Okay, our next presenters is the team from Atelier 10. We have Jessica, Sundberg, Zofchak, and Michael Esposito. And Jessica is a senior environmental designer at Atelier 10, manages a number of highly ambitious local and international projects. Jessica works as a technical lead within the environmental design and daylighting practice at Atelier 10, focusing on integrated and computational methods for building performance optimization. Her recent focus includes developing Atelier 10's in-house daylight and facade optimization toolset. She holds a bachelor's degree of science in building technology, a degree in marketing science, and master's of engineering in high-performance structures from the Massachusetts Institute of Technology, and currently serves as a lecturer for the daylighting at the University of Pennsylvania. Michael, as a technical staff at Atelier 10, he supports a large range of projects from environmental design, energy analysis, daylight, and benchmarking work. He brings an analytical perspective to the firm and utilizes this in the development of in-house analysis tools, as well as investigating the latest green technologies. Michael has expertise in building envelope analysis and facade optimization. He holds a bachelor's of architecture from Cornell University, and his research interests relate broadly to sustainable design, with topics of interest including the use of computation and energy daylight simulation in the design process. Prior to working at Atelier 10, he worked at the Cornell program of computer graphics under the direction of Donald Greenberg and Kevin Pratt, developing tools and processes for parametric energy simulation. And the title of their presentation is A New Look at Resiliency, Modeling Temperature Drift with Microbes. Is that it?
Yep, great. So, long, wordy title, but welcome, everybody. Thank you. We are from Atelier 10, as Karen said. We're a group of about 100 people internationally. Basically, environmental designers, people who work in optimization, energy modeling, as well as out of London, full MEP design, and our New Haven office, lighting design as well. And while our adoption of DIVA has mainly been for a lot of the facade optimization on the daylight visual comfort side of things and pulling in the solar information, today we're going to present on our adaptation of it for the use with the Viper tool. We're going to talk about an urban green study that we had participated in conjunction with them before, hot off the press about 2 weeks back, the Resiliency study, which we'll talk a little bit more about. We'll discuss the methodology for modeling, why was this really Viper the best tool to use here, our findings and next steps from that study, and then we want to throw out there the idea of a possible resilient building benchmark, and our first steps at looking at what that would mean. So with resiliency, there's this new hot topic with climate change. This is a graphic from the Urban Green Report that starts to track some of the larger climate events in the New York metro region over the past few years. Some of these not being quite scaled for, this is Superstorm Sandy right there, for the actual impact on our region and our city. And we want to start to look at resiliency as not just an issue for the overall urban context, the large flooding we had, large natural disasters, areas being wiped out, but what it also means down to the building scale itself and resiliency within buildings. And then what is that relationship back to high-performance buildings in general? What are the linkages there, that in the overlap we see within those two? So Urban Green, you've probably heard of them for the Green Building Task Force that they put together to kind of propose building codes, updated building codes for the city. The most recent task force they put together is this Building Resiliency Task Force, which was teamed to look and really research this topic of resiliency post-Sandy and what that would mean for the city. They came together. We are part of the overall larger team. You saw many of the names before on that first slide. Well, came up with general recommendations, about 18 in total, that outline building and citywide or urban scale design measures to enhance the potential for resilient design of the city there. And it focused on retrofits for commercial, multifamily residential, and the smaller home scale. And they really tagged all the different aspects here. Stronger buildings, how do they build those initially more resilient there? Backup power, how do we deal with long-term outages? Backup means for that. Essential safety, really life safety here. Survival as well. And then better planning. So in the future, how can we be more prepared for such disasters? Just a snippet of some of the summary pages you'll see in the kind of executive summary of the report. The commercial project with a bunch of the highlights there, multifamily residential, the scale of what that would look like, and homes as well there. Essential safety is really what we focused on as our part of this project. We looked at how can these buildings or retrofits really provide shelter, a safe, survivable condition without any power at all. So that's where you see the temperature drift come into this. We were tasked to look at the standards and critical strategies for maintaining resilient design. In terms of the envelope, we looked at the improved insulation, high-performance windows, air tightness, thermal mass, benchmarking. How do we look at the existing building stock and really determine where we're at? How close are we to succeeding on this? How much work really needs to be done? And then we verified through simulation, which is what we'll go through a little bit later with the Viper tool. How can we really maintain these habitable temperatures? And I guess another important thing to add here is a lot of the outcomes we saw from this in terms of those envelope improvements and the things we outlined for resilient aspect of things were also very much in line with what we saw for just good high-performance building design. And it was nice to follow off the momentum of the Superstorm Sandy to kind of get that into people's minds and get people thinking about that. And this was a very timely report, I think, for what we were dealing with here. These were the four types. So we looked at modeling the wood frame housing, masonry, multi-family row house, the low-rise, and then the high-rise construction for apartment buildings. And the assumptions for these baseline models were taken from another urban green study, the 90 by 50 report, which looked at reducing carbon emissions for the building stock of New York City by 90% by 2050. I'm missing the slide on that, but that is where our main baseline assumptions for these different scenarios in our model came from. And then we looked at higher levels of building performance, so that's our baseline. Where do we measure beyond that from existing codes or proposed codes or just general pushing things to the limits of the high performance construction there. On the data side, the weather data coming into these models, we looked at basically the two worst case scenarios, so either extreme heat or extreme cold for the region. January, we looked at the classic TMY3 file you'll see in the light blue. We looked at the historical data from 2012, or I guess 2011, 2012. And then we also had considered for a while, just in the previous presentation, the use of a future climate file, and was that something that was appropriate for this case. At this point, we just picked out, you see here, for the January file, the real kind of worst succession of low temperature days there, and the inverse for July weather. So we picked a period there highlighted that had sort of the constant high temperatures, and we'd see those worst case conditions. And then in the end, we'll see more graphs later, but we would have the high performance case, an ASHRAE 2010, the upcoming code case. We have the 2007. A lot of us benchmark our buildings on that versus LEED nowadays, the 2007 model. And then the current existing building stock. And then you'll see in the graph the actual outdoor temperature and what we're trying to offset there. So, turn this over to Mike.
So this was kind of our maiden voyage for the use of Viper and Viper component in Grasshopper. Is that any better? Good. Okay. The scope of our analysis for this was to look at different performance criteria in relationship to actually 5 different residential apartment types. And so the DIVA Voivod component within Grasshopper lends itself to that. We were able to set up this whole study parametrically and also link with Excel for both the input and the data visualization in the end. Talking about process and workflow, this looks very familiar to a daylight kind of parametric setup with the input on the left, the main geometry translation components in the middle, the building description components, and then the export. Here it is simplified. You'll see we added the Excel input and the Rhino input, as well as the batch driver on the left side. Then we decided, well, a lot of the parameters for this study dealt with numbers that were best handled in Excel through spreadsheets. So having that component and that ability to link and update Excel and have it relink to the Grasshopper file was pretty critical to the study. These are the 5 discrete zones that we tested. Very simple shoe boxes of different sizes. And then sorry, wrong button.
You have to click it again, I think it's the button.
Okay.
Do it here.
Oh yeah.
Click it? Yeah.
Yeah. We control the variation within the model using 3 parameters. One was the building type, which you can see selecting between the building, the single zones. The other was the standard, so existing stock versus hash rate 90.1 2007, 2010, and then a projected improvement. And what that one did was it actually selected a series of values from a list from Excel, different infiltration rates, different R value, and so forth. And then there was a final component that tested orientation, so south, west, and north. And in the end, there was 60 different models. We found it very easy to customize the material selection and even select different material choices based on those parameters we defined in the beginning. We did have to go in through the IDF to create some custom adiabatic materials, but for the most part it was very easy to parametrically test different materials, especially with kind of the set R value opaque wall component. We did not find it so easy to turn off the HVAC, for example, or adjust some of the schedules. At that, you definitely had to leave Grasshopper and go in through the IDF folders on the C. But in the end, it wasn't very difficult either. We used the holiday schedule and linked it to the HVAC operation schedule to turn off the HVAC during those extreme periods. And then we scheduled nighttime ventilation during the summer, which was just as easy of a fix. The batch driver component was one thing we developed that really helped automate through each 60 models and export and sequence. Really just a time saver with a kind of trigger component that just double click and set a multiple at once. Findings and next steps. So unlike most energy models that we do that look at loads or energy use intensity, this one was really concerned with monitoring the temperature within the apartment over the specified period when the HVAC system was turned off. So above, you're looking at heating energy, bottoming out at 0 during that period. This is in the winter. And then below that, you're looking at the temperature drift. You'll see it approaching the outdoor air temperature. In those 3 different, the purple, teal, and green, are showing different performance criteria. So whereas you can review or view all these results within the component, we are really just kind of looking at the indoor air temperature and outdoor temperature. Let me get a quick drink. With most studies, and this one included, we like to perform sensitivity studies to begin with. One, to validate that the model is performing as would it be expected. So this was one of them, where we tested different infiltration rates and the effect they had on the indoor air temperature. As you would expect in the winter, infiltration rate has a huge impact on that temperature drift within the space. So this helped us to kind of understand the results of the other multi-parameter simulations. And then here, this is another sensitivity study that looked at the effect of thermal mass, and in the summer this had a huge effect on tempering the solar gains. So this is a south-facing apartment, and this is kind of showing those peaks in solar gains corresponding to the indoor air temperature peaks. This is a sample of some of the results. This was for a high-rise masonry building facing north, which was a worst-case scenario for the winter. Looking at this being an estimate of the current New York City building stock for this apartment type, and then looking at these three different standards. And really the concern, we shied away from really coming up with a threshold for what is the absolute minimum that you would want the temperature to reach, because it's a very complicated number to come up with. It has a lot to do with how long you're in that space at that temperature, clothing, age, and so forth. Kind of similar to that glare study that Olson did, where there's always that one dissatisfied person and the other person that's, can put on some clothes. This was the summer case. Again, kind of confirmed that the improved standards, including exterior shading on a south-facing apartment, really helped to reduce that peak temperature drift during the summer period. These bands here correspond to the nighttime ventilation, so the building zone is able to cool off at night. And then our key findings, were more in kind of what you would expect in terms of improved insulation, high-performance windows and shading, air tightness and thermal mass, increasing the ability of the building to maintain habitable temperatures without HVAC. We also found that New York City's existing building stock is most at risk in the event that power goes out, in terms of temperatures falling below healthy survivable temperatures. And then another thing was we kind of realized that there's value in simulating without HVAC and designing a space to perform without HVAC and maximizing that period. Some of our comments on the Viper tool, and we've used it since for other studies, is that it's great for these parametric geometry studies, but sometimes it can be difficult to edit schedules. It has a limited set of output variables. One thing we would have liked to add to this to kind of complete the thermal comfort narrative is heat radiant temperature and relative humidity. So these things were a little harder to come at parametrically. And that leads into the difficult to assess the holistic thermal comfort of the model.
So ultimately, this brings us to the question of, with this information and with this proposal to the city, what can we really do with this in terms of promoting this passive building design or really resilient buildings? And is that defined by daylight access? During the day, if we all are in our homes or offices and we are in this maybe semi-long-term power outage, can we have daylight to function for these tasks? Egress, do we have the right means to get out of these buildings in emergency situations? Permeability of water, this is a near and dear to my heart photo from Hoboken, New Jersey, where I live, from Hey Sandy. How can we really look at that around buildings? And then the most important thing we focus on here, the thermal stress and comfort. How can we adapt this to really become a set of benchmarks or modeling standards that is really wrapped into the workflow for most projects or ongoing projects? We thought, how does maybe could apply to a system similar to the Appendix G modeling guidelines for the code standard buildings. But what's that metric for comparison? Here we've used comfortable hours or temperature, but that doesn't work with our current practice of energy cost comparison. And should it be performative or prescriptive in its matter as well? And then, like Mike was saying, what are really the physiological limits of the human body? Can a person withstand maybe more sporadic times of extreme weather, whether that's hours or days? Or is the limit also just within a withstanded period of time of those conditions? And how do we look at the atmospheric comfort zone? How is that defined for different climates and different, worldwide? How can this be adapted to really be looked at under different cultural conditions and things like that? And then where do we draw that line of what's really comfortable versus what's survivable and really functional for a human being? So we've kind of looked at 4 things here. This was a study done to assess passive strategies, looking at a baseline condition, adding some summer shading for the external window openings, and then natural ventilation, how those temperatures are brought more into those green comfort bands with each of those measures. And then that's translated to more of a binary timeline for your hours of the year, and whether or not you're comfortable. It would be green for you can work within that environment, or white, you're outside of the comfort range. And like I said before, what becomes a survivable window of time and what's really unacceptable, and how can we start to chart that out. So this is one way of looking at it. There's the Universal Thermal Climate Index, more of an outdoor metric right now, takes into account direct solar, temperature, relative humidity, wind speed, things like that. It rates your hours, so these are plotted hours over the month, from extreme heat stress through a comfortable no thermal stress condition through to your extreme cold stress. Maybe that can be adapted so that for really survivability, we're talking about you're either comfortable or you're semi-comfortable, or it's a kind of dead zone beyond that, your extreme periods. And maybe as you add in more passive measures to the envelope of your building, you can get rid of those issues on the perimeter of your survival situation. And while you also do those things like adding shading or using natural ventilation, you increase the number of comfortable hours there as well. And how can this apply comparatively for different climates? Maybe your baseline survivable hours you need to achieve is much smaller in New York. You just have some extreme heat, some extreme cold. But in an area of Las Vegas, maybe there is more extreme heat to overcome. Maybe that's, if you can achieve all those hours, that's your baseline. You've achieved the baseline in this benchmarking system. And maybe a percentage hours beyond that, getting those into a comfortable situation might be the next step in that rating system. Kind of like you have your lead levels, maybe the system has some sort of threshold that's building on how much more comfortable are you making people in these buildings for these non-power situations. And lastly, the psychrometric chart, we have our comfort range here. Maybe this is where you really want to be. That's the ideal situation if all of your hours can be within that. But then you can maybe have a semi-comfortable zone where people start complaining, but they can, if you're trying to make it day to day and you can survive in those conditions very comfortably. And then maybe you have exactly the survival condition. And the goal of the system would be then to get all of these points outside of that dotted red line within there in order to achieve a baseline performance for a building for survivability for this resiliency. And what is the shape of that? We just have this drawn on diagrammatically. We need to define that. That's something that I think is really cross-disciplinary. We need to pull out to the health industry, really see where these limits are and how that would work. But again, just a proposal and a thought. So with that, we just like to kind of see that we've tried to set some kind of minimum compliance for resilient building performance, and I think the city is now with this task force trying to move in that direction. But how can it serve the existing buildings versus new construction? That's yet to be told. Again, defining those limits for the human body for survival is the underlying factor of it all. And then how can we also look at stable climates versus diurnal swings? How is that going to affect the recommendations that might be in this benchmarking set? And then crossovers between passive design strategies. I think there's a lot of things that if you're doing this to increase the survivable condition, you're also going to be increasing the building performance day to day. So it's kind of a win-win. So with that, any questions? Yes.
I guess on the level of survival, you say that we're always thinking about the drastic extreme. And in terms of what we're willing to put up with at extremes, on a day-to-day basis, we go to work and we're in an office building and we expect, AC and light and, to be in a comfortable situation. But then you go to the survival side and not to go way to an extreme, but like say, for example, when you go camping, you're willing to deal with, a couple mosquito bites and, a slightly warmer climate. So what is that extreme that you're going with when you say survival? Like, what is that?
Well, I think the question is very similar to those of us who've been in New York or the Northeast the last couple, week or so. Maybe day 1 or day 2 would have been uncomfortable, but we could have managed it. But maybe the heat exhaustion versus day 3, day 4, day 5 becomes the point where, people start dropping like flies because it's just no longer comfortable. You can't function in the basic human things of moving maybe from space to space or, smaller tasks. I mean, if we're in this kind of condition, the city might, or the context you're in might shut down, the world might change in their behavior for that period of time. Similar to Sandy, we saw shutdowns across the city for a while. Maybe we're not trying to keep it so that people can function in the way that they had done the day before, but it's trying to define that to a more, I guess, expanded range, and we haven't drawn those lines yet.
Actually, just kind of to answer his question, we are actually trying to conduct a thermal comfort survey in our office. We always keep recommending extended comfort ranges, and that kind of developed a need, and we have wired our office to know it actually right now. And we are taking all the data in terms of when the windows are open, what are the fan speeds. There are 6 people in our office, so we've actually seen some decent results for last year or so. Now we're actually going to extend it and one of a few of our partner offices, some architects and whatnot. But we are actually looking forward to that range where what are those extremes?
Yeah.
So hopefully soon.
Yeah, and I think that range you're defining is really kind of that semi-comfortable we're considering. So it's not the standard office, very controlled condition, but it is that open range where you can kind of come and go, and you can get some nice breeze from a window and things like that. Yeah.
If you look this up, there's a dissertation that recently was published at the GSD by what's the woman's last name?
That's what I'm wondering. Huang
something. But it has a really good analysis. I think a really comprehensive analysis of different comfort metrics and screen these things.
I think the thesis was the first published North American author from the comfort studies.
Yeah.
The last name is Huang, so.
Okay.
Is that the first handle?
No, everyone calls it by his last name.
Great.
And also a tool that comes out of MIT in a few weeks that was developed by Les Norford and Bueno, and we tested it for design. It's called the Urban Weather Generator, and that generates urban heat aspects. So if you have a climate file, it basically gives you a modified climate file that takes extra snow, humidity, and temperature into account.
Question for Michael. Were you having any issues with working on the same idea with the idea editor and Viper? Like, was it reverting some of the things you were custom editing, or on the other side, were you able to pull in your custom objects from the editor back into Viper?
Yes, there were limitations, and sometimes I didn't know what I did wrong, but I knew I did something wrong, and I had to revert back. But for the materials, it was pretty easy to know that I had to edit, say the shared folder. But for others, it was trial and error, honestly.
Definitely give a shout out to Emily Hagan in our office, who was the driving force behind most of this work and with Urban Green. Okay.
Could you talk to us a little bit more about the batch generator, like how you guys are using that? I see that it's triggering the simulation and it's writing.
Yeah.
Sequentially. Are you using that to write the simulations and then run them at a later time, or is it sequentially just running?
No, that would be nice. It's sequentially running them. It's really just animating through every single combination of parameters and exporting them in sequence. These were simple models, so they only took about 2 minutes to simulate at most. So it's very quick to do it that way. But it would be nice to write it and then simulate.
Any other questions? No? Thank you very much.